Okay, so at the previous lectures, we considered mostly operators on arbitrary Banach spaces. And today we concentrate on operators on a Hilbert space. From the viewpoint of operator theory, one of the main advantages of Hilbert spaces is that if we look at the algebra B of H of bounded operators on a Hilbert space, then this is not just an algebra, and it's not just a Banach algebra. This algebra carries one more algebraic operation, the so-called involution or the joint operation. And the presence of this operation makes operator theory on a Hilbert space much richer than the operator theory on general Banach spaces. In particular, it leads to the important notion of a self-adjoint operator, which is important not only in functional analysis and not only in mathematics, but also in quantum mechanics. So today our main goal will be to prove the famous Ilberschmitt Theorem, which completely describes the structure of compact self-adjoint operators on a Hilbert space. First of all, let's recall some standard facts about Hilbert spaces. Let's recall that if H is a Hilbert space, then we have a canonical bijection R between H and H star, the dual space, which takes each element x in H to the functional fx on H, given by the inner product with x. And this map R from H to H star is an antilinear isometric bijection. So this result is the Riesz representation theorem on linear functionals on the Hilbert space. Okay, now let's take two Hilbert spaces, say H1 and H2. And suppose that T is a bounded linear operator from H1 to H2. So let's look at the following picture. First we have the dual operator, T star, which acts from the dual space H2 star to H1 star. Also we have the canonical bijections, say R2 from H2 to H2 star, and R1 here. And since R1 and R2 are bijections, we can there is a unique arrow from here to here. There is a unique map from H2 to H1, which makes this diagram commute. So let's temporarily denote this operator by T plus. This operator, T plus, is called the adjoint of T. So by definition, the adjoint of T is the map T plus from H2 to H1, given by the following formula. T plus is R1 inverse, T star R. In other words, this is the unique map which makes this diagram commute. Adjoint in Russian is сопряженный. Сопряженный оператор. Поскольку двойственные иногда тоже называют сопряженным, чтобы не путать, иногда это называют Гильбертовым сопряженным. Okay, so what can we say about the adjoint operator? Let's observe that the adjoint operator is also a bounded linear operator from H2 to H1, and its norm equals the norm of T. Well, indeed, it is linear because T star is linear and these two maps are antilinear. So it's clear that the composition of a linear map and two antilinear maps is linear. And it is bounded and its norm is equal to the norm of T because R1 and R2 are isometric bijections. So the norm of T plus equals the norm of T star, but we already know that the norm of T star equals the norm of T. This operator T plus can also be equivalently described in the following way. Proposition 1. So this is an equivalent characterization of the adjoint operator, which doesn't involve dual spaces. So I claim that T plus is a unique map from H2 to H1, which satisfies any of the following equivalent conditions. Any, and hence all, because they are equivalent, of the following equivalent conditions. Condition 1, the inner product of Tx and y equals the inner product of x and t plus of y for each x in H1 and y in H2. And an equivalent condition 2, the inner product of t plus and y, t plus y and x equals the inner product of y and tx. Well, indeed, but it's so. First of all, it's almost immediate that 1 and 2 are equivalent. This is clear because our inner product is Hermitian. So this number is just the complex conjugate of this one, and this number is the complex conjugate of this one. So 1 and 2 are equivalent. And let's now show that condition 1 is equivalent to our initial definition of the adjoint operator. Well, indeed, 1 can be equivalently written as follows. So the left-hand side of this formula is the functional R2 of y applied to T of x. And the right-hand side of this equality is equivalent to the following. This is the functional R1 of T plus of y applied to x for each x and y. Now we look at the left-hand side of this formula. So this is a functional applied to T of x. And by the definition of the dual operator, this is nothing but the functional T star of R2 of y applied to x by the definition of the dual operator. So now when we compare this and this, so these two numbers should be the same for each x and each y, we conclude that this is equivalent to the statement that T star composed with R2 equals R1 composed with T plus. And since R1 is a bijection, we can equivalently write this as follows. T plus equals R1 inverse, T star R2. And this is nothing but our original definition of T plus. So this completes the proof. Well, of course, T plus and T star are not the same operator. They are different. Actually, they act between different spaces. T star acts between the dual spaces, and T plus acts between H2 and H1. But nevertheless, since R1 and R2 are isometric bijections, it follows that the properties of T plus are almost equivalent to the properties of T star. For example, T plus is invertible if and only if T star is invertible. T plus is, say, topologically injective if and only if T star is topologically injective, and so on. And because of this, we adopt the following standard convention. So from now on, the joint operator T plus will be denoted by T star. Well, of course, this is an abuse of notation, but usually it doesn't lead to any confusion. So it's a more or less standard convention. When we speak of operators on the Hilbert space by T star, we always denote, by default, we always denote by T star the joint operator. Not the dual operator, but the joint operator. Okay, let's now discuss some properties of our new operation, namely the operation of taking the joint operator. So this is our proposition 2. First of all, this operation is antilinear. So if we take a linear combination of two operators, lambda s plus mu t, then the joint of this operator is lambda bar s star plus mu bar t star. Here, S and T are operators, and lambda and mu are complex numbers. By the way, let's recall that the operation of taking the dual operator is linear, but the operation of taking the joint operator is antilinear. This is important. Second, if we have two operators S and T, say S acts from T acts from H1 to H2 and T acts from H2 to H3, then the adjoint of the decomposition equals T star S star. So here T acts from H1 to H2 and S acts from H2 to H3. Property 3, if you take an arbitrary bounded operator between the Hilbert spaces and take the adjoint twice, then you get T. And because of this, the operation of taking the adjoint is sometimes called the involution, because it is indeed an involution in the set theoretic sense. The square of this operation is the identity map. Property 4 was already mentioned before, but for completeness, let me write it once again. The norm of T star equals the norm of T. And finally, property 5 is the following identity. The norm of T star T equals the norm of T squared. So again, here T is a bounded operator from H1 to H2. So the left-hand side is, of course, well-defined because T star T is an operator from H1 to itself. This identity is sometimes called the Sistar identity. And in fact, axiomatizing all these properties leads to the very important notion of a Sistar algebra, which we will probably discuss a bit later in our course. Well, the proof of, for example, properties 1 and 2 easily follows from similar properties of dual operators. Parts 1 and 2 follow from similar properties of dual operators. Well, indeed, property 2 is immediate from the respective property of the dual operators. And here we have a slight difference, namely the operation is not linear but is antilinear. And the reason is clear. If we come back to this formula, we see that after we multiply t by lambda, so T star will be multiplied by lambda, but because R1 is antilinear, we can take lambda from here, and it will be lambda bar here. And this is the reason why this operation is antilinear. Property 3, maybe the best way to deduce property 3 is to look at our proposition 1. So proposition 1, the uniqueness of the operator T plus and proposition 1 readily imply that T del star equals T. Property 4 was already mentioned before at the top of that blackboard. So let's prove the Sistar identity, property 5. Well, first of all, if we look at the norm of T star T, we know that the norm of the product of two operators is less than or equal to the product of their norms. So we have this inequality. And since the norm of T star equals the norm of T, this is the norm of T squared. And now we have to prove the opposite inequality. And to prove the opposite inequality, we'll calculate the norm of T in terms of the inner product. So the norm of T squared is the supremum over the closed unit ball of the norm of T of x squared, which is the inner product of Tx by itself. This is just the definition of the operator norm. Well, now we use our proposition 1. So we take T from here to here, and it will be T star. So this is T star T applied to x, and the inner product with x, the supremum over the unit ball. And now the Cauchy-Bunyakovsky-Schwarz inequality implies the following. This is less than or equal to the supremum over the unit ball of T star T x. Multiplied by the norm of x, but the norm of x is less than or equal to 1. So we can write this inequality. And this is nothing but the norm of T star T. So we get the opposite inequality. Okay. Here's another simple but useful property of joint operators, proposition 3. Suppose that T is a bounded operator from H1 to H2. Then, first of all, I claim that the kernel of T star equals the orthogonal complement of the image of T. Second, the orthogonal complement of the kernel of T star equals the closure of the image of T. And finally, H2 is the orthogonal direct sum of the closure of image of T and the kernel of T star. And this is the orthogonal direct sum. That is, the summands are orthogonal to each other. Well, the simplest way to prove this is to recall similar properties of dual operators. So the formulas were exactly the same. They had slightly different meaning, namely the kernel of the dual operator equals the annihilator, in that case the pre-annihilator, or the annihilator of the image of T. But we know that under the canonical bijection between Hilbert space and its dual, the orthogonal complements are mapped exactly onto annihilators. And so properties 1 and 2 are immediate from the similar properties of dual operators. 1 and 2 follow from similar properties of dual operators. Of course, it's also very easy to prove them explicitly. It is almost, they are true almost by the very definition of the joint operator. And formula 3 follows from 2 and from the orthogonal complement theorem. So this is the orthogonal complement of this, and by the orthogonal complement theorem, their direct sum is exactly H2. Okay, from now on, we concentrate on a special class of operators on Hilbert space, namely on self-adjoint operators. So suppose that we have a Hilbert space H, and a bounded operator T on H. So in this case, the joint operator is an operator on the same Hilbert space. And we say that T is self-adjoint, or Hermitian, if T equals T star. Sometimes it is useful to consider a more general class of operators, the so-called normal operators. So we say that T is normal. T is normal if T commutes with T star. Well, of course, each self-adjoint operator is normal. This is clear. But of course, the converse is not true. For example, if you multiply the identity map by I, the imaginary unit, then the resulting operator will be normal, but will not be self-adjoint. So observe the following obvious characterization of self-adjoint operators. A bounded operator T on H is self-adjoint if and only if the inner product of Tx and y equals the inner product of y of x and ty for each pair of vectors in our space. And of course, this is a special case of our proposition 1. So this identity means exactly that T equals T star. So as a result, we get the following almost trivial, but in fact very useful property of self-adjoint operators. One more proposition. Proposition 4. Proposition 4. Suppose that T is a self-adjoint operator on the Hilbert space H. And suppose that H0 is a closed T-invariant subspace. Closed T-invariant vector subspace. Then the restriction of T to H0 is also self-adjoint. Is a self-adjoint operator on H0. And this readily follows from this characterization. Of course, if this formula holds on H, then the same formula holds on H0. And by the way, a nice exercise is to study if the same result holds for normal operators. This is a question. Self-adjoint operators have many nice properties. For example, we have the following result. Let it be theorem 1, which is quite important. If T is a self-adjoint operator on a Hilbert space, then the spectrum of T is real. The spectrum of T is real. By the way, in some sense, self-adjoint operators can be considered as operator analogs of real numbers. So if we interpret operators on a Hilbert space as non-commutative analogs of complex numbers, then the self-adjoint operators will play the role of real numbers. And we will see numerous results which emphasize this analogy several times. So this is one of them. The spectrum of a self-adjoint operator is real. By the way, in quantum mechanics, operators are extensively used in quantum mechanics. Usually they are not bounded, but for unbounded operators, it's also possible to introduce the notion of a self-adjoint operators. And unbounded self-adjoint operators are interpreted as observables in quantum mechanics. That is, those physical things which we can measure somehow, such as the momentum, velocity, and so on. And the spectrum is interpreted as a set of those values which can be actually measured. So if we have a self-adjoint operator, then the spectrum, the set of values which you can measure, is contained in the real numbers. Okay, suppose that lambda is a point in the spectrum. So let's write it as alpha plus I beta, where alpha and beta are real numbers. And so we want to show that beta is 0. We want to show that beta is 0. We do the following trick. We take an arbitrary real number, little t, and observe that lambda plus I t sits in the spectrum of the shifted operator t plus I little t 1, just by the definition of the spectrum. Okay, so this implies that the modulus, the absolute value of this number, lambda plus it, is less than or equal to the norm of our operator. This is the general property of the spectrum. For each point in the spectrum, the absolute value is less than or equal to the norm. So we take the square of this number, and we calculate the right-hand side by using the Sistar identity. So we must multiply the adjoint of this operator by the operator itself. But the adjoint of this operator is t minus I little t1, because t is self-adjoint. And we should multiply it by the operator itself. So this formula holds by the Sistar identity. And when we multiply these two expressions in brackets, we get t squared plus a little t squared 1. So by the triangle inequalities, this can be estimated as follows. Well, on the other hand, the left-hand side of this inequality can also be calculated explicitly. So the square of the modulus of a complex number is the sum of the squares, the sum of the square of the real part plus the square of the complex of the imaginary part. So the real part here is alpha, and the imaginary part is beta plus t. And so explicitly, this is alpha squared plus beta squared plus 2 beta t plus t squared. And we know that this number is less than or equal to this number. Okay, we can now cancel t squared from here and from here. And we conclude that alpha squared plus beta squared plus 2 beta t is less than or equal to the norm of t squared. And this inequality holds for each real number t. So we see that the left-hand side of this expression, which is a linear function in t, is bounded from above. And of course, this is possible only if this function is constant. That is, if and only if beta is 0. But this is exactly what we wanted to show. So we see that the spectrum of a self-adjoint operator is real. Okay, here is a useful corollary. Suppose that T is a self-adjoint operator on a Hilbert space. And suppose that we have two eigenvectors, x and y, in H. So they are eigenvectors of T. In other words, there exist numbers lambda mu such that T of x equals lambda x and T of y equals mu y. And we suppose that the respective eigenvalues are not the same. And I claim that in this case, the respective eigenvectors are orthogonal to each other. the eigenvectors corresponding to distinct eigenvalues are orthogonal to each other. Well, the proof is very easy. We simply calculate the following expression, the inner product of x and y multiplied by lambda. So what is this? This is the inner product of lambda x and y. Now lambda x is t of x, but t is self-adjoint, so we can move t from here to here. This is the inner product of x and t of y. T of y is mu y. So now the inner product is antilinear in the second variable. So this is the complex conjugate of mu multiplied by the inner product of x and y. And now we recall that mu is in the spectrum because it is an eigenvalue. So it is real. So now we compare this and this. So since lambda is not equal to mu, this equality can happen if and only if the inner product of x and y is 0. That is, x is orthogonal to y. Okay, one more important property of self-adjoint operators, theorem 2. For technical reasons, we will prove it in a slightly more general context of normal operators. So suppose that T is a normal operator on a Hilbert space. I claim that the norm of T equals the spectral radius of T. Let's recall that in a general case, the spectral radius is less than or equal to the norm. So this holds for each bounded operator on each Banach space, and in fact for each element of a unital Banach algebra. But for normal operators, these numbers are equal to each other. The spectral radius equals the norm. To prove this result, we observe, first of all, that for each self-adjoint operator S, for each self-adjoint operator on H, we have the following equality. And this is just a special case of the Sistar identity. And I claim that the same result holds for normal operators. So we now observe that T star T is self-adjoint. This is true for each for every bounded operator. If you take the star of this, we get the same operator. So this operator is always self-adjoint. So we apply this equality to T star T, and we get the following. The norm of T star T squared equals the norm of T star T squared. Now we apply the Sistar identity again to the left-hand side of this equality. So by the Sistar identity, we see that this is the norm of T to the power of 4. And now let's look at the right-hand side of this equality. So what is this? So this is T star T, T star T. But T is normal, so we can interchange these two operators. And we see that this is T star squared, T squared. or equivalently t squared star t squared. And finally, we apply the Sistar identity once again, now to the operator t squared. And we see that this is the square of the norm of the operator t squared. Okay, now we compare this and this. We take the square root, and we see that we have the following inequality. And now we just use the inductive argument. We apply the same to the operator t squared, and so on. And we see that the same formula holds for each power of 2. And now we calculate the spectral radius by using the Gelfand formula, which looks as follows. This is the limit of the following sequence. So this is a general result which holds for each element in a unital Banach algebra, and in particular for each operator on the Banach space. And of course, we can take the limit over the subsequence of the powers of 2. So this can be written as follows. But because of the previous line, all the members of this subsequence are the same, and they are precisely the norm of t. And that's it. So we see that the spectral radius equals the norm. Okay, so if we now combine theorem 1 and theorem 2, we get the following corollary. Suppose now that T is a self-adjoint operator on the Hilbert space. Then the spectrum of T is contained in the closed interval of the following form. So from minus the norm of T to the norm of T. And moreover, at least one of the endpoints of this interval belongs to the spectrum. So either the norm of T is in the spectrum, or minus the norm of T is in the spectrum. Well, indeed, the first part, this inclusion, follows from the fact that the spectrum is real, and the spectral radius is less than or equal to the norm. And the second statement follows from the fact that the spectral radius is exactly the norm. So we cannot replace this interval by a smaller interval, by a smaller symmetric interval. So this is the smallest symmetric interval. I mean, by symmetric, I mean symmetric, so in the following sense. So this is the smallest interval of this form, which contains the spectrum. So at least one of the ends is in the spectrum. Okay. Okay, let's now prove a useful property of invariant subspaces of self-adjoint operators. Well, first of all, we have following proposition. Suppose that T is a bounded linear operator on a Hilbert space, and as H0 is a closed vector subspace of H. I claim that this subspace is T invariant. H0 is T invariant, even only if the orthogonal complement is T star invariant. So this useful relation between invariant subspaces of an operator and of its adjoint. The proof is straightforward. So for convenience, let's start with the second statement. So the orthogonal complement is T star invariant, even only if for each element x in H0 and for each element y in the orthogonal complement, the following number is 0. Well, this means exactly that T star of y sits in the orthogonal complement to H0. That is, the orthogonal complement is invariant under T star. Well, but what is this? This is nothing but the inner product of Tx and y. And to say that this is 0 is the same as to say that for each element x in H0, the vector T of x is orthogonal to each vector in the orthogonal complement. So formally, this means that T of x sits in the double orthogonal complement. But of course, we know that the double orthogonal complement is H0 itself, because H0 is closed. And so we get the statement that H0 is T invariant. H0 is T invariant. And for self-adjoint operators, we get the following corollary. Suppose that T is a self-adjoint operator on the Hilbert space H. And suppose that H0 is a closed vector subspace. Then H0 is T invariant, even only if the orthogonal complement is T invariant. Okay, so these are the basic properties of self-adjoint operators. We will come back to self-adjoint operators a bit later. And now we concentrate on compact self-adjoint operators. Compact self-adjoint operators. So our main result here will be the Ilberschmitt Theorem. So we start with the following lemma. Suppose that T is a compact self-adjoint operator on a Hilbert space H. then the norm of T is the maximum eigenvalue of T. So more exactly, this is maximum of the absolute values of lambda, where lambda runs over the point spectrum. That is the set of all eigenvalues of T. The proof is a combination of our previous results with the Ries-Schauder theory. Well, indeed, we know from the previous lecture that the spectrum of T is almost the same as the point spectrum after we, actually they will be the same after we throw away 0. This was proved at the previous lecture, and this holds for each compact operator. So this holds for each compact operator on the Banach space. So now the norm of T, since T is self-adjoint, the norm of T equals the spectral radius. And the spectral radius, when we calculate the spectral radius, so by definition the spectral radius is the following number. But because of this equality, we can replace the spectrum by the point spectrum here. And the result will be the same. So the norm is the modulus of the maximal eigenvalue of T. Okay, so now we are ready to discuss the Ilberschmitt theorem. Well, maybe. So for technical reasons, I'd like to use a separate part of the blackboard for this result. So the Ilberschmitt theorem. The original statement of this theorem didn't involve any operators. Hilbert and Schmitt worked in the context of real Hilbert spaces and quadratic forms. But after some observations of Ries, this theorem was translated into the language of operators. So suppose that T is a compact operator, is a compact self-adjoint operator on a Hilbert space. H is a Hilbert space. Then there exists an at most countable orthonormal family say EI in H. So since it is at most countable, we can assume that I is either a set of real numbers, of natural numbers, or the finite set from 1 to n. And of course, there is also the general case where I is empty. This case corresponds to the zero operator. such that the following conditions are satisfied. Condition 1, each vector in this family is an eigenvector of T. And this corresponding eigenvalue is real and non-zero for some non-zero real number lambda I. Second, the orthogonal complement of the set of all these vectors is precisely the kernel of T. This is the orthogonal complement of this family. So basically, these two statements completely describe the behavior of our operator. So it acts as a diagonal operator on the linear span of, on the closure of the linear span of this family, and it is 0 on the orthogonal complement. Moreover, property 3, the respective eigenvalues lambda I. So this set is exactly the set of all non-zero eigenvalues. So this is the point spectrum minus 0. Property 4, of course I don't claim that all the numbers lambda I are distinct. More exactly, if you take an arbitrary non-zero eigenvalue of T, an arbitrary non-zero eigenvalue lambda, we have the following equality. So the number of occurrences of lambda in our sequence equals the multiplicity of the respective eigenvalue. The multiplicity is the dimension of the respective eigenspace. So each non-zero eigenvalue appears in our sequence as many times as the multiplicity of lambda is. Property 5, if our family is infinite, that is, if I is the set of natural numbers, then the respective sequence of eigenvalues goes to 0. And finally, a useful formula, formula 6. This is the so-called Hilbert-Schmitt decomposition. For each vector x in our space, g of x equals the following sum. Lambda I the inner product of x and ei and ei. This is the so-called Ilberschmitt decomposition. Of T. Well, there are many statements here, but essentially, if we forget about some details, essentially the theorem states that our operator can be written in the following block matrix form. So on the closure of the linear span of these vectors ei, it looks like a diagonal operator. So we can write such an infinite matrix here. And on the orthogonal complement, it is identically 0. So this result essentially generalizes the well-known statement about self-adjoint operators on a finite-dimensional Hilbert space, which you probably know from your linear algebra course. Okay, let's now prove the Ilberschmitt theorem. First of all, to prove the first part, to construct this orthonormal family EI, we do the following. For each lambda, let H lambda denote the respective eigenspace of T, the kernel of T minus lambda. So this is defined for each complex number lambda, but of course it is non-zero. If it is non-zero, that lambda is real and it is in the point spectrum of T. And let L denote the closure of the algebraic sum of all eigenspaces corresponding to non-zero eigenvalues. The closure of the algebraic sum. And again, of course, we can consider only those lambdas which are in the point spectrum. So this is called the vector subspace of H. So we know from the Rischauder theory that each summand here is finite dimensional. Each summand is finite dimensional, and that the point spectrum is at most countable. So this follows from the Rischauder theory, which was discussed at the previous lecture. And this holds for each compact operator on an arbitrary Banach space. Okay, so let's choose an orthonormal basis in each summand. Let B lambda be an orthonormal basis of H lambda for each non-zero point lambda in the point spectrum. So it is finite, because the space is finite dimensional. And let B denote the union of all these bases B lambda. Now, since the eigenspaces corresponding to distinct eigenvalues are orthogonal, this is one of our previous results. They are orthogonal. This implies that that B is also an orthonormal family, and in fact it is an orthonormal basis of L. So B is an orthonormal basis of L. And finally, since each B lambda is finite and the point spectrum is at most countable, we conclude that B is at most countable. Excuse me? B lambda is finite. B lambda is finite because B lambda is a basis of H lambda. H lambda is finite dimensional. So we take the union of countably many finite sets. Okay, so B is at most countable. So we can write B in the following form. EI, where the index set big I is most countable. So I is either the set of natural numbers or the finite set from 1 to n, or the empty set. And by construction, for each I, we have the following formula. So our set B consists of eigenvectors of T, and moreover, lambda I is non-zero, because we considered here only eigenspaces corresponding to non-zero eigenvalues, and lambda I is real because the spectrum is real. So each lambda I is on zero real numbers, either a non-zero real number, because the spectrum is real. Okay, so this proves the first part of our theorem. Now we have to show that the orthogonal complement is precisely the kernel of T. First of all, it's clear from our construction that L is a T-invariant subspace. L is T-invariant by construction. Each eigenspace is invariant, and the closure of the sum of invariant subspaces is invariant. T is self-adjoint, so the orthogonal complement is also T-invariant. The orthogonal complement is T-invariant, and T restricted to the orthogonal complement is still compact and self-adjoint. Well, indeed, the restriction of a compact operator onto any subspace is compact, and we have just proved that sometime about 15 minutes ago that the restriction of a self-adjoint operator onto an invariant subspace is also self-adjoint. So it is also a compact self-adjoint operator on the orthogonal complement. But what can we say about the point spectrum of this operator? So all eigenvectors of T corresponding to non-zero eigen values are in L. So L orthogonal doesn't contain any of such eigenvectors. And this implies that by construction, we see that the point spectrum of T restricted to the orthogonal complement of L is, well, it is either empty or zero. It doesn't contain non-zero numbers. But then the spectral radius is zero, and so the norm is zero by our lemma. So our previous lemma implies that the norm of this operator is zero. That is, the operator T restricted to this subspace is zero. So we see that the orthogonal complement is contained in the kernel. The orthogonal complement is contained in the kernel. And now to prove that this is exactly the kernel, we take an arbitrary vector in the kernel, and we observe that since T of x is zero, the inner product of Tx and EI is also zero, simply because the T of x is zero. Well, now T is self-adjoint, so we can move T from here to here. This is the inner product of x and TEI. And since TEI is lambda I EI, and lambda I is real, we can write this in the following way. And now since lambda I is non-zero, and the whole expression is 0, we conclude that x is orthogonal to I. For each I. Which means that the kernel is contained in the orthogonal complement. So combining this and this, we conclude that the second part of our theorem is proved. So the kernel of T is exactly the orthogonal complement. Okay, now let's now observe that parts 3 and 4 are emitted from our construction. Well, indeed, we constructed our family in such a way that each non-zero eigenvalue sits in the set, because we took all non-zero eigenvalues there. And moreover, since the orthonormal basis of each h lambda is contained in L, we conclude that each eigenvalue, each non-zero eigenvalue, appears in the set as many times as the dimension of h lambda is. This is exactly the multiplicity of the respective eigenvalue. So this follows from our construction. Now, property 5. Well, let's assume that this is not the case. So suppose that lambda I doesn't converge to 0. Well, in this case, we can find a subsequence which converges to non-zero complex numbers. To a zero complex number. There is a subsequence, say lambda ik, such that this subsequence converges to a non-zero number mu. Now this is more or less clear. First, since this sequence doesn't converge to 0, first we choose a subsequence which is separated away from 0, and then by compactness we find another subsequence which converges to a non-zero number. Also, we observe that this sequence doesn't stabilize. The sequence doesn't stabilize by property 4. So each element of the sequence appears only finitely many times in this. Oh, I forgot to add one more important point. The space is finite dimensional. This was already mentioned at the very end of the proof, at the very beginning of the proof. Look, so h lambda is finite dimensional. So of course we include this in the statement for convenience. So each lambda appears in the sequence only finitely many times, and so the sequence doesn't stabilize. But this implies that mu is not an isolated point of the spectrum. So mu is in the spectrum because the spectrum is closed. But mu, now we see that mu is not an isolated point. It's a limit point of the spectrum. This is contradiction because we know that each non-zero point of the spectrum of a compact operator is an isolated point. So this is a contradiction with the Riesz-Schauder theory. And this completes the proof of part 5. So lambda I converges to 0. And finally, to prove part 6, so we take any element x in our space. So T of x, of course, sits in the image of T. The image is contained in the closure of the image. And we already know that the closure of the image for each bounded operator is nothing but the orthogonal complement of the kernel of T star. This holds for each bounded operator, but T self-adjoint, so we can remove the star here. So this is the orthogonal complement of the kernel. But we have already proved that we have already proved this. So the orthogonal complement of the kernel is the closure of the linear span of this family. This is the closure of the linear span of the family EI. This holds by formula 2. These vectors EI is an orthonormal family. They form an orthonormal family. So we can write T of x just as the sum of its Fourier series. T of x is the sum of the Fourier coefficients multiplied by EI. And again, we essentially now repeat the same calculation as before. I mean this calculation. So this Fourier coefficient is, because T is self-adjoint, this is the inner product of x and TEI. And TEI is lambda I EI. And finally, since lambda I is real, we come to the following formula. And this is our Hilbert-Schmitt decomposition. Okay, so this completes the proof of the Hilbert-Schmitt theorem. So in conclusion, let's formulate an important but special case of this result. It corresponds to the case where our Hilbert space H is infinite dimensional and separable. So first of all, we give the following definition. Suppose that we have two operators on Hilbert spaces, S and T. So here H1 and H2 are Hilbert spaces. And suppose that U is a unitary isomorphism between H1 and H2. A unitary isomorphism. That is a linear bijection. A linear bijection which preserves the inner product. We say that U is a unitary equivalence. U is a unitary equivalence between S and T if the following diagram commutes. So this is S, this is T, and this is U. So essentially, this means that H1 and H2 can be identified in such a way that S becomes T. And if such an operator exists, we say that S and T are unitarily equivalent. If such an operator U exists, then we say that S and T are unitarily equivalent. So a corollary of the Ilberschmitt theorem, an important special case. Well, a corollary which is actually a little exercise for you, but it is very easy. It easily follows from the theorem. Suppose that T is a compact self-adjoint operator on a separable infinite-dimensional Hilbert space H. Then T is unitarily equivalent to a diagonal operator, say M alpha, on the little L2 space. And moreover, the respective sequence alpha sits in C0. It vanishes at infinity. The proof follows from the Ilberschmitt theorem. So we take first this orthonormal family EI, and then we take an arbitrary orthonormal basis in the orthogonal complement. So when we take the union of these two bases, we get an orthonormal basis of the whole space. It is at most countable because the space is separable. And if you now identify H with little L2 by means of this basis, we easily see that our operator T becomes the diagonal operator. So each element alpha of the sequence is either one of the elements lambda I or just 0. So it sits in C0. Finally, well, if you don't mind just a couple of minutes, I give a very short but important example, which shows that the Ilberschmitt theorem doesn't hold for non-compact operators. An example and a simple exercise at the same time. So we consider the following operator on the big L2 space or square integrable functions on the interval 0, 1. So the operator T is just the multiplication by the coordinate. Then it's easy to see that T is self-adjoint, but the point spectrum is empty. So this example shows that the Ilberschmitt theorem doesn't hold for non-compact self-adjoint operators. Excuse me? Yeah, of course, but but the diagonal form, of course, is still preserved. This doesn't hold, of course, for the identity operator. But for this operator, it's impossible to find such an orthonormal family that 1 and 2 holds, because, the point spectrum is empty. So if 1 and 2 were true, then T would be 0 just because of 2. Fortunately, there is another important result. So there is a special way to generalize the Ilberschmitt theorem, to reformulate it in such a way that this more general form will hold for all bounded self-adjoint operators. And the respective result is called the Spectral theorem for self-adjoint operators. This result will be proved in the end of our course. And that's all for today.